Hello, as part of my doctoral research, I will be presenting a predictive maintenance system that we developed. To begin, I would like to open the application and simulation to provide some context. When addressing the problem, industrial machinery, especially large-scale equipment, can cause significant losses if a failure occurs. These losses may include replacement costs, production downtime, service interruptions. To mitigate such risks, there are various maintenance strategies, with predictive maintenance being the focus here. Predictive maintenance involves monitoring machinery using sensors and analyzing this data through technologies like machine learning and big data. The aim is to prevent failures or, at the very least, provide early warnings, allowing for proactive measures. In our study, we developed a predictive maintenance system leveraging IoT devices. Let me walk you through the components of our system. System overview. As you can see, we have here a few modules. One of them is data collection. Our data comes from IoT devices running on the Contiki NG operating system. Since these devices have limited processing capabilities, data is exported via REST APIs for further analysis. We focused on ensuring seamless data transfer, which I will explain in another video. You can see here our business process. Data collected from IoT devices is routed through an intermediary like Apache Kafka. Thought this module is optional, it becomes necessary when dealing with large data volumes. You can see here Contiki NG operating system and the data collection module, REST APIs, and we can get this data from this module with REST APIs, and we have Apache Kafka as a messaging system. As I said, this module, this Apache Kafka messaging module is optional. It becomes necessary when dealing with large data volumes. For our simulation, we don't need this module. You can see here a few modules. One of them is messaging. One of them is anomaly detection module, fault prediction module, and remaining useful life prediction module. We save our data in PostgreSQL database. The first module is anomaly detection module. Incoming data is processed to identify anomalies. Data is labeled based on these anomalies using Java and Moa library. While we process streaming data, a database stores data for model training purposes. And fault prediction module. Using the labeled data, this module classifies and identifies pre-failure conditions. It doesn't stop at anomaly detection, as not every anomaly leads to failure. Instead, it focuses on predicting pre-failure states for actionable insights. And remaining useful life prediction module. To estimate the time left before a failure occurs, we use deep learning models developed with Python, Keras, and TensorFlow. These provide a valuable timeline for taking corrective actions. Each module in the system has been developed and validated independently with results published in conferences and journals. The end-to-end workflow. The data flow in our system is as follows. IoT data is collected from devices using Contiki-NG operating system. This data is processed in real time to detect anomalies. Identified anomalies are analyzed to classify pre-failure conditions. Finally, the rule is predicted, enabling timely actions. While the simulation runs, I will provide further details. IoT data collection module. This module handles incoming IoT data, which is then processed for anomalies. And classification module, once data is labeled, it identifies the potential failures and generates actionable results. Although results are displayed as a text, this method has limitations in terms of readability and usability. As you can see here, results are displayed as text. This method has limitations in terms of readability and usability. Therefore, we need provenance integration. Understanding and trusting the system's decision is critical for users. To address this, we integrated a provenance mechanism into our system. Here you can see our modules are running. IoT data collection has been completed. Clustering is completed, and classification is completed. We need to have a remaining useful life value and an action. After we get remaining useful life estimation, then we prepare the action. This is a simulation environment for users. As I said, the text is not so readable, so we need provenance integration. So what is provenance? It tracks the history of data, transformations, and decisions. This ensures transparency and accountability, which are crucial for user confidence. And visualization, provenance data is not just stored, it's also visualized as a graph, allowing users to trace decision paths, view model performance, and understand actions taken. So we have here a generate provenance button. When we click this, then we get a provenance graph generated by our system dynamically. So you can see here the action is created, and the remaining useful life is estimated. So our environment, our simulation environment is running, and predictive maintenance system is running. But as I said, we need data provenance integration to visualize these actions and to give the users some trust for these decisions. So we generate provenance, and the provenance data will be generated dynamically. The graph will be generated. Let's see the provenance generating. Our provenance is generated. Let's open the provenance graph generated by the system. The graph dynamically illustrates there are some parts, the agents, activities, and entities. Agents are responsible. It can be user or software. They are responsible for activities. Activities, they are processes executed within the system. And entities, they are data inputs and outputs from these activities. When we look at the graph, we can see IoT data is processed into actionable outputs. So IoT data is generated by data collection and used by data processing, and processed data is generated and derived from IoT data. And you can see here relations between activities, agents, and entities. And you can see the history of the data and all the actions. To make the system domain specific, we extended the standard provenance ontology schema with attributes like model performance metrics, training and testing dataset details, frameworks, algorithms, and hyperparameters used. These extensions allow users to trace every decision and its underlying data, verify model accuracy and configuration, evaluate rule predictions and the actions derived from them. You can see here the action is generated, maintenance record is generated, and system administrator can take this action. The action has some values, the action type, stop the machine, action target is machine 7. You can see the action and the other steps executed. In our simulation, IoT data is collected and processed, anomalies are detected and labeled, pre-failure conditions and rules are predicted, maintenance actions are proposed. And you can see here the attributes we added. Model name is the model, the algorithm. Here is Hofting 3, for example, and the metrics, the performance metrics, and the framework used, the model type used, version, training data size, test size, hyperparameters. So you can see all other informations about models or about the decisions. You can see also the values for other models. For example, remaining useful life model generation. The remaining useful life model has some attributes, the model name, the performance metrics. This is for deep learning algorithms, and the other informations. Also for clustering model, you can see the cluster is the algorithm name, and the clustering measurement performance metrics. So you can see all the data. We have also, as to validate the system, we conducted a user studies comparing traditional logs with provenance-based visualizations. Results showed that provenance significantly improved user trust and efficiency in identifying data source, decisions, logic, and actions. Our system offers an integrated approach to predictive maintenance, combining IoT, machine learning, and provenance for transparency and accountability. Future video will be explore specific modules and user study details. Thank you for listening.